Welcome back to the channel. Rocaford FPV and more here, and if you've been following along with our videos, we have been setting up a custom 2.5-inch build on ArduPilot. In the last video, we set up the optical flow sensor, we tested out loiter mode indoors, and we saw towards the end of the video that the barometer was starting to struggle indoors because of some of the pressure changes from the prop wash off of the walls. In this video, we're going to take a look at this barometer issue and come up with ways that we can fix the barometer when we're not able to use the rangefinder. I've done a test flight off screen. I loaded up the log in UAV log viewer, so let's go ahead and take a look at some of the data. We scroll down, Baro 0, we can take a look at the barometer readings. We have altitude and pressure. So here we can see the pressure is spiking on takeoff, and that's the ground effect that we're seeing, and the altitude drops for the reading. Then we switch to out hold mode, and we can see the barometer readings are seemingly consistent along with the pressure readings. But looking at the vehicle, as I'm giving it pitch and roll commands, the vehicle is actually descending, so let's see that in the logs. If we come down in CTON and select desired altitude, and throttle out, you can see that the throttle out is relatively consistent in altitude hold mode. Along with that, if we go down to RCN and we plot the throttle, you can see that I'm leaving it in the mid-range value for altitude hold. But here we can see if I plot C1 and C2, you can see the pitch and roll commands that I'm giving the vehicle. Coming down to the RFND 0, we can see the rangefinder readings. So you can see here, as I'm giving the vehicle pitch and roll commands, the vehicle is actually descending. This is a sign of an exposed barometer being susceptible to pressure changes, even though the pressure readings appear consistent on the data logs. And then you can see the vehicle wanting to correct the desired altitude as the vehicle is actually descending. So let's take a look at how we can fix this. Okay, so after taking a look at the logs, we can see what an exposed barometer does for the vehicle's ability to hold its position vertically. What we're going to do is we're going to take the frame apart. We're going to put some of this open cell foam over the barometer, and we're going to take a look at how this improves the ability for the vehicle to hold its position. In order to install the foam correctly, we need to know where the barometer is. So on the MECO Air H743V2 all-in-one, we're looking at the diagram here for the board, and the barometer here is in the top corner where the arrow is, on the side where the SD card slot is, and the boot button. So in our particular build, this is facing up, so it needs to sandwich between the board and the top frame. All right, we have the frame taken apart, and I have some of the bolts taken out so I can get to the bottom part of this. Now, we could have done this during the initial build, but what I wanted to do was show how the exposed barometer actually affects flight and how the open cell foam covering the barometer improves the flight and the ability for it to hold its altitude. All I'm going to do is slide this under the motor wires underneath the flight controller, and then I'm going to secure everything back together. Okay, if you can see in here, I have the foam slid underneath the board right here. All I'm going to do now is bolt it back together. Okay, I'm back with the assembled frame. I have the open cell foam installed covering the barometer, so let's do a test flight and we'll see how this does. Now that we have the foam covering the barometer, I did a test flight indoors with similar pitch and roll commands as the first test flight with the barometer exposed. So let's go down and check a couple of these fields. We'll go down to RCN, and we're going to plot C1 and C2. These are the pitch and roll commands. C3, you can see in out hold mode, the throttle is in mid position, so we can remove this. Let's go down to the rangefinder and plot the rangefinder reading. So you can see as I'm giving the pitch and roll commands, the rangefinder is keeping a pretty consistent altitude, so the foam appears to be doing its job by allowing the vehicle to maintain a consistent altitude as I'm giving it commands indoors. So head on over to Google and type in ArduPilot temperature calibration. Click that first link and you'll go over to the ArduPilot page on the temp calibration. It's going to give you information on what temp calibration is, why it's done, and how to do it. Essentially what's going to happen is the vehicle is going to be exposed to different temperatures, whether you're flying in winter, summer, you have your VTX on or off, and other pressure changes that are going to introduce variables to the sensors. So the idea of the temperature calibration is to provide offsets for all temperatures that the IMU might be exposed to in all flight conditions. All right, let's take a look at how to do this in Mission Planner. So in the full parameter list, we're going to search for tcal_. We're going to set options to both checkboxes, and then we're going to do tcal enabled, enable and learn, write parameters, and then refresh the parameter list. Now we're going to come back over to the search box and type in ins_tcal, and we're going to enable the temperature calibration for IMU1, and we're going to enable for IMU2. Write parameters. Okay, our parameter list has refreshed. Scroll down to ins_tcal1 tmax and tcal1_tmin. So we need to set the minimum and maximum temperature ranges for the calibration process for each IMU. For the minimum, we want to think about the coldest winter day we're going to fly on. In order to reach this kind of temperature on our desk in a controlled environment, we're actually going to throw our vehicle into the freezer, which reaches about -18 degrees Celsius. So we're going to type in -18 here. And then for the Tmax, we need to think about the hottest summer day that we're going to fly on with our VTX powered on. 70 degrees Celsius should cover about most hot days I'm going to fly on. In order to reach this kind of temperature in a controlled environment, I'm not going to use the VTX because I don't want to burn it just sitting here. I'm going to use a heat gun instead. Let's come down to TCal2 Tmax and TCal2 Tmin. And we're going to set the same thing, -18 and 70. Now we're going to write parameters. The next time we reboot the vehicle, the temperature calibration process is going to start automatically. So what I'm going to do off screen, I'm going to put the vehicle in a freezer for an extended period of time, maybe 30 minutes to 90 minutes, and then I'm going to come back and I'm going to show you how this is done. Okay, I pulled the vehicle out of the freezer. I didn't get to leave it in as long as I had hoped for. Hopefully it got cold enough. We're going to see how it works. So what I did is I plugged the USB cable in first, and now I'm going to plug it into the computer. One thing to note is once the temperature calibration starts, you do not want to move the vehicle at all on the table. You want to leave it still. So let's plug it in and connect. Once we're connected, I'm going to come down to the messages tab. So the messages tab is getting spammed with these EKF3 IMU messages. The temperature calibration takes about 10 minutes and a message will pop up when it's completed. I'm going to give the vehicle a few minutes to warm up on its own, and then I'm going to introduce a heat gun to start simulating hotter temperatures. Okay, let's just go ahead and introduce the heat gun. So I'm just using this portable heat gun. I'm going to turn it on and I'm going to point hot air towards the IMU to start heating up the temperature. We see temperature calibration completed. We can go to the config tab and take a look at the full parameter list, and we can type ins_tcal and verify that the temperature calibration completed. So here we see values in the tcal1. Scrolling down, we see values in tcal2, and here tcal1, tmax, and tmin have been auto-populated, so -2.5 degrees Celsius up to 70 degrees Celsius. So we weren't able to reach the -18 degrees Celsius from the freezer. I did pull it out early, so this is likely why. And then similarly for tcal2 max and min, we have -0.82 and a max of 70. So the heat gun did simulate a hot environment without having to burn our VTX out. Let's take a look at the IMU temperature calibration page. And if we scroll down to the offline calibration tool section of the page, we can see charts of uncorrected and corrected behavior for the gyro and for the accelerometer. Come down here to the key features of the graph. A good calibration, we will see corrected lines close to 0. Going over to UAV log viewer for our recent log where we had the barometer covered, let's go down to IMU 0. We'll plot gyro X. You can see some variance around 0, gyro Y, and gyro Z. Now let's take a look at a recent flight we did after the IMU temperature calibration. I've already loaded this up in UAV log viewer. Let's go down to IMU 0, gyro X, Y, and Z, and we can see that the data plotted indicates a good calibration. Now that we've completed our IMU temperature calibration, we're going to go to the full parameter list and we're going to set up some parameters to reflect the physical positioning of our optical flow sensor and rangefinder on the actual vehicle. So we're going to go to flow underscore. You're going to look for flow position X. On my build, the optical flow sensor is about 35 millimeters behind center, and it's about 10 millimeters down from center. Then we're going to go RNG FND1 underscore. Our rangefinder is about 2 millimeters off the ground, 45 millimeters behind center, and 15 millimeters down from center. The optical flow sensor is already working in loiter mode, but we need to calibrate it so it can work even better. Go to Google and type in ArduPilot optical flow calibration. Click on that first link and it's going to take you to ArduPilot's page for the optical flow sensor testing and setup. On this page, it's going to walk you through the in-flight calibration. It does require a GPS though, and since our 2.5 build doesn't have a GPS, we're going to have to do it the manual way. Scroll down to the log-based calibration. Essentially what we're going to do is turn on the vehicle, we're going to hold it level, and we're going to rotate it on the pitch axis and the roll axis. Then we're going to download and take a look at the logs, and hopefully we'll be charting logs that look something like this, and if they don't, we're going to start adjusting some parameters. Okay, so we're back in Mission Planner and we need to set up parameters in order to get ourselves ready for the offline optical flow calibration. So let's search log underscore disarmed. The default value is 0. We're going to set this to 2. What that means is we're going to log while we're disarmed except when we're on a USB connection. Right parameters. Now I'm going to go outside and find a place in my backyard that has good texture and good contrast. I'm going to plug in my vehicle, wait for it to boot up. Then I'm going to pick the vehicle up in my hand and I'm going to rotate it on the pitch axis about 10 times. And then I'm going to rotate it on the roll axis about 10 times. Then I'm going to unplug the vehicle, come back in and take a look at the logs. Okay, I'm back inside. Let's scroll over, hit data flash logs, review a log. We'll load up the optical flow data that I just collected. And then we're going to come down to OF. We're going to chart flow X and body X. Let's zoom in here. Now you can see the manual rotations that we did. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 axis rotations that we did. These are lined up pretty well, so I don't think I need to do any calibration. Now with the flow X and the body X were off, then I would need to play with the FX scalar parameter to get these to be lined up. Another thing that we're going to need to look for is the body X versus the IMU. So let's uncheck flow X, come up to IMU, and plot the gyro X. Let's zoom in here. If these were out of sync, then we would need to do some more tuning of parameters to get them to be in sync. But these look good, so I'm not going to do anything. Coming back over, we're going to look at the flow Y and the body Y. Let's zoom in here, and these look good too, so I'm not going to do anything more here. Okay, now let's go back into Mission Planner and turn log disarmed off. In the full parameter list, search log underscore disarmed, and we're going to set this back to 0, right parameters, and then we're going to search for EK3 underscore IMU, and we're going to set the mask to only use the first IMU. Since we're only using a barometer, we're not using GPS, a single IMU is enough for our purposes. We'll write parameters. Another parameter parameter we're going to want to change is the surface tracking. So if we type in surf, come down to surf track mode, I like to turn this off. When it's on, the vehicle is going to detect obstacles beneath the vehicle and then adjust the altitude accordingly. So if I'm flying indoors and I'm flying over a table, the vehicle is going to climb on its own. So if it's at 1 meter before the table, it's going to fly 1 meter over the table. That's not the behavior that I want, so I'm going to turn off surface tracking and write parameters. Then we're going to come over to RNG_use. These two parameters allow me to tell ArduPilot to use the rangefinder instead of the barometer under certain conditions. So the barometer is the default EK3 source 1 altitude source, but we can say if the rangefinder is within, let's say, 95% of its effective range, we can use the rangefinder as long as the vehicle is not moving any faster than, say, 0.5 meter per second. What this says is if the vehicle is generally still, use the rangefinder to maintain its altitude. If the vehicle is moving, then use the barometer. The right parameters. A question you might be having at this point is why don't we just set the EK3 source Z to rangefinder instead of using barometer the whole time if there's so many issues with the barometer? Well, the answer really lies with the limitations of the rangefinder. So with this rangefinder, we only have an 8 meter maximum range, and that's on paper. So we may actually see less range depending on the quality of the rangefinder that's on this build. Since it's an MTF-01, I would expect that the quality is a little bit cheaper than, say, a $250 OpFlow. So I did a test flight outdoors using the rangefinder as the primary altitude source, and let's take a look at what happened. Let's scroll down to the CTON and take a look at the throttle out. So I took off in stabilize mode, and then I switched to loiter, and then I went back to stabilize mode. This doesn't really tell you anything until I start plotting more data. So let's go down to the rangefinder. So if I plot the distance of the rangefinder, you can see that as I approach a certain altitude, the rangefinder actually stops providing data because we've exceeded its range. But let's add one more data point to tell the whole story. So let's go back up to the RCN and let's plot throttle. So here the green line is the throttle. So as I'm taking off, I'm giving it throttle. I've stabilized a bit, and then I'm trying to increase throttle, and I'm trying to increase throttle a little bit more. And here the rangefinder is maxed out. So the rangefinder is not providing any more data. The motors aren't providing any more thrust, but my throttle stick is actually all the way up. So I'm telling the vehicle to climb, but it won't climb because the rangefinder has exceeded its maximum range. So ArduPilot's refusing to increase the altitude. To show this even further, let's go over to stabilize. So now we're not using the rangefinder anymore, and let's come up to CTON and plot altitude. So here the red line is the altitude, where you can see that the rangefinder wasn't providing any data. I was giving throttle max to try to increase altitude. ArduPilot was saying, no, I'm not going to give you more altitude. And then as I switch into stabilize mode, it's not using the rangefinder anymore. My throttle stick is going up a little bit, and the altitude is increasing. So this is a very big reason why I don't want to set the rangefinder as the primary EK3 source for Z. Instead, I'll use the barometer and then rely on the rangefinder using those two values that we just set for the use range and use speed. That wraps up this video. In the next video, we're going to set up Lewis scripts to run the LED flash patterns and servo for the tilt cam. So stay tuned for more. Thanks for watching.